Today we're going to discuss about permutations. What you're going to expect in this lesson, you are going to define the permutation of n objects to solve problems using different rules of permutations. So let's explore first permutation. So what do you think are common in these examples? A, B, C, D, E, and so on. 1, 2, 3, 4, 5, 6, and so on. First, second, third, fourth, and so on. RT1, RT2, RT3, and so on. XXL, XLL, M, S. Yes, it is arranged in order. So what is then a permutation? So a permutation is of the set of objects is an ordered arrangement of the items, where order is important. So there are different formulas in getting the permutation. So if it is a permutation of n different objects taken R at a time, this is the formula. N factorial over n minus 1 factorial. That exclamation point is what we call factorial. And we will discuss later how to solve that if we have that symbol. So we have here the second one, permutation with identical objects. So this is the formula. N factorial all over n sub 1 factorial times n sub 2 factorial, and so on. The third one is circular permutation. When you are going to have a circular permutation, this formula is used to find the statistics of permutation of distinct objects arranged in a circle is given by this formula, n minus 1 factorial. So we have factorial notation. How do we solve factorial notation? So when we say the product of 4 times 3 times 2 times 1 can be written simply as 4 factorial. So when we say 4 factorial, it is the same as 4 times 3 times 2 times 1. 5 factorial, 5 times 4 times 3 times 2 times 1. 10 factorial, 10 times 9 times 8 times 7 times 6 until 1. Okay? So let's have examples. So example number 1 about permutation of n different objects taken R at a time. So we have to evaluate this one. If you see an example or like this, you will use the permutation of n different objects taken R at a time. So again, this is in letter A, it is read as the permutation of 8 objects taken 4 at a time. So how do we solve that? So that means n there is 8, R there is 4. When you substitute the formula, so 8 minus 4, that is 4. So we'll just copy 8 factorial over 4 minus 4 factorial. Again, when we say 8 factorial, it is 8 times 7 times 6 times 5 times 4 factorial. Why until 4 factorial? So we can cancel out 4 factorial in the denominator and the numerator. So what's left there is 8 times 7 times 6 times 5, which is equal to 1680. How about letter B? 10, the permutation of 10 objects taken 2 at a time. So substitute the formula. So 10 factorial over 10 minus 2, that is 8. So 10 times 9 times 8 factorial over 8 factorial. Cancel 8 factorial. So what's left is 10 times 9, which is 90 rather. Number 2. This is a permutation of n different objects taken R at a time. A class is to select a president, a vice president, a secretary, and a treasurer from 7 class members. How many arrangements of class officers are possible? So we select a president, a vice president, secretary, and treasurer from 7 members. So n is equal to 7. R is equal to 4. Why 4? 1 president, 1 vice president, 1 secretary, 1 treasurer. It is equal to 4. So using the formula, n is 7, R is 4, so substitute 7 minus 4, that is 3. So 7 factorial over 3 factorial. 7 times 6 times 5 times 4 times 3 factorial all over 3 factorial, so cancel out 3 factorial. So what's left is 7 times 6 times 5 times 4 equals 840. This kind of example is or can be solved also using the fundamental principles of counting. We have there 4 events, like we select a vice president, a president, a secretary, and treasurer. So there are 4. So in the first event, there will be 7 class members to choose from. If you have already a president, to the next number, how many persons to choose from? There will be 6, right? Because you have already a president, so president will not be elected anymore for vice president. There will be 6 class members to choose a vice president. So 6, 5 secretary, 4 treasurer. So when you multiply that one, that is equal to 840. Therefore, there are 840 possible arrangement of class officers. Example number 3. Permutation with identical objects. Let's try to figure out when can we use the permutation with identical objects formula. The covered walk of a school is to be lined with flags. How many different arrangements are there of the 10 flags if 5 are blue, 3 are red, and 2 are white? So in here, so the solution we have, or the given here, we have 10 and sub 1, that is the blue flag, and sub 2, that is the 3 flag, and sub 3, that is the 2 flag. You can assign n sub 3 as the blue flag. It's up to you, and so on. So the formula is n factorial over n sub 1 factorial times n sub 2 factorial times n sub 3 factorial. Substitute. So 10 times 9 times 8 times 7 times 6 factorial, 5 factorial, all over 5 factorial times 3 factorial times 2 factorial. Cancel out there 5 factorial of the numerator and the denominator. So what's left in the numerator? We have 10 times 9 times 8 times 7 times 6 over 3 factorial over 2 factorial. When you solve that one, that is equal to 2520. So there will be 2520 different arrangements of 10 flags, with 5 are blue, 3 are red, and 2 are white. Example number 4, permutation with identical objects again. So how many different 9-letter words, it could be real or imaginary, can be formed from the letters in the word committee? So in given here is 9. Why n is 9? Because there are 9 letters in all in the word committee. N sub 1 is 2. Why n sub 1 is 2? There are letter M, we have 2 letter M's, right? So that is why n sub 1 is 2. N sub 2 is also 2 because there are other 2 letters which are doubled or T. 2 T's there, so that is 2. N sub 3 is 2. What is that 2? That is the 2 E's. Right? Those are the letters which are identical or the same. So we can use the formula, substitute n, which is 9, n sub 1 which is 2, n sub 2 which is 2, n sub 3 which is 2. So 9 factorial, that is 362,880 all over 2 factorial times 2 factorial times 2 factorial, that is 8. When you divide, equals 45,360. Therefore, there are 45,360 different 9-letter words. Example number 5. This is a permutation of n different objects taken R at a time. Rabin has 9 distinct mathematics books and 5 distinct science books. The shelf has space for only 7 books. If the 4 positions are to be occupied by mathematics books and the last 3 by science books, in how many ways can this be done? So in this given problem, there are 2 permutations. The permutations of the mathematics books and the permutations of science books. So you are going to multiply the 2 permutations. So the permutations of the mathematics books, which is 9 books, permutations of 9 mathematics books taken 4 positions at a time, multiplied to the permutation of the 5 science books, taken 3 at a time. So substitute 9, and there is 9 over 9 minus 4 times 5 factorial over 5 minus 3. So you will multiply the two permutations. So what is 9 minus 4? That is 5. So copy 9 factorial over 5 factorial times 5 factorial over 5 minus 3, that is 2 factorials. Cancel 5 factorials in the numerator and 5 factorial in the denominator. What is left there is 9 factorial over 2 factorials. So when you simplify that one, that is 181,440. Let's have circular permutation. So in this given example, you can determine if the permutation to be used is circular permutation if it talks about circular objects. So in here, find the number of circular permutations of 7 dancers. The formula is n minus 1 factorial. Substitute n, which is 7, minus 1, that is 6. 6 factorial, or 6 times 5 times 4 times 3 times 2 times 1, that is equal to 720. So there are 720 circular permutation.